What I intend to do today is, first of all, go over assignment 2 with you, or answer your questions, any questions you have about that assignment, and then talk about measurement validity, but to a greater extent, measurement reliability. And let me say at the outset that topic, validity and reliability, is not covered in the text. So if you have questions, I'll take them, but hold them until I have an opportunity to do that in an orderly way. Let's talk about assignment 2. Are there any questions about any part of that assignment? Yes.
My question was kind of about how, when I found the variance, I used my husband's statistic book, which is actually a harder class because it's for business, but the way they explained this was a lot easier than the book we have now, and I kind of did it according to how they said to do it, and so I wanted to know if...
You need to hold it down. Yes.
Is it not working? I'm holding it.
Anyway, okay.
At any rate, so on a test, are you going to look at our work and how we arrived at the answer, or does it matter? Or
There are multiple, even in this, the question really pertains to the way in which variance and standard deviation are discussed. That some texts make it appear, present a clearer discussion than other texts. And they offer different computational procedures. I don't mind which text you use to come to an understanding of those concepts or any of the issues that we discuss in class. The second issue that you raise, the one regarding computation, is an important one because on the exam, there will be a series of 3 questions. One that pertains to the numerator in the computation of variance, one that pertains to the denominator, and then one that asks you for the variance score. And you need to use formula 4.3, 4.4 in the text to do that, because those will be the formulae that I will use. And as I tried to indicate last time, I believe that those formulae are themselves informative. Informative, first of all, because they tell you something conceptually about what variance is and what standard deviation is. And secondly, because they tell you how to compute those scores. Let me deal with the issues specific to assignment 2 and handle those sorts of issues separately. Are there any? Yes.
As far as like the standard deviation go, you know how you're supposed to do the deviation in order to get the variance. So if we had to do the sample variance and you talk about the standard deviation, we only do the sample deviation instead of just both?
It does not matter in this assignment. I'm not concerned whether you compute population variance, sample variance, population standard deviation, or sample standard deviation, as long as you understand what you're doing and why you're doing it. That is, if you're computing, you should understand first that if you've computed population variance, that the population standard deviation is simply the square root of that population variance score. Similarly, if you've computed sample variance, then the sample population is simply the square root of that sample variance score. You should also understand that if you've computed population variance and standard deviation, you should have used n as the denominator. And if you've computed sample variance and standard deviation, that you should have used n minus 1. Beyond that, I'm not concerned at all. In fact, I've posted both solutions, both the population scores and the sample scores.
I was just going to say, for those, can you go over the answers or tell us what they are?
I don't have those with me, and what is more, I simply don't have those answers with me, but you can access those on WebCT. I will say that I'm not concerned, and you shouldn't be concerned, primarily with the accuracy of your answers. You should be I'm concerned, and to some extent, therefore, so should you become concerned, with understanding the process by which you derive those answers. Are there any questions about the computation of measures of central tendency or measures of dispersion as applied to those 90 scores on page 37? If there are none, that is, if there are no questions, let me move on to a discussion of the next topic on the syllabus, and that is two related issues: measurement reliability and measurement validity. Measurement reliability and measurement validity. And what you will discover is that, as just an overview comment, you will discover that much more of our discussion concerns measurement reliability than measurement validity. And the reason for that is that the measurement reliability is so much easier to assess and control. Let's start this discussion with a couple of questions. If you look at your watch and it says 9:07, what is the time? This is not a trick question. You know, when I came to this country, people say there's a foreigner. We can say, who's in Grant's Turret in Grant's Tomb? But this is not a trick question. When you look at your watch, it says 9:07. What do you believe to be the time? 9:07. If a police officer pulls you over and tells you that you were going at 84 miles an hour, how fast do you believe you were going? 84 miles an hour. If you put a thermometer in your mouth and hold it there for the requisite amount of time and take it out and it says 99.5, what do you believe your body temperature to be? 99.5. Well, whatever the time is, I will bet you it's not 9:07. I will bet you weren't going at 84 miles an hour, and I will bet you that your body temperature is not 99.5. I may be wrong in some instances. You may happen to have a thermometer or a speedometer, whatever it is, a measuring device that is error-free, or one in which the error components cancel themselves out and have generated a perfectly valid score. But the likelihood of that happening is almost zero. It's essentially zero. What we have to distinguish between are observed scores and true scores. And the scores that you and I deal with, the readout on our speedometer, the readout on the thermometer, the readout on the watch, the readout on the scales, weight scales in our bathroom, are all observed scores, you would agree. And those observed scores are estimates of true scores. And you and I are forced to treat those two as if they are equivalent. We are forced, that is, to treat observed scores as if they are equal to true scores. Sometimes it becomes apparent even to you and I that that is not the case. Some of you have watches that mysteriously gain 15.5 minutes across any 24-hour period. And you know then that these observed scores, these estimates of true scores, estimates of true time, are incorrect. Some of you have a set of scales, bathroom scales at home that have been handed down from generation to generation. They're now 26 years old. You step on them and they just, the arrow never stops. And you know that those observed scores then are inaccurate or include error. You make this argument explicitly to instructors on occasion. You take an exam, you get the exam back, you look at your score on it, and you say, but I know more than that. And you go to the instructor and you say, I know more than this. Can I take it again? Can I take another test? Because I know more than this. What you're arguing is that the observed score on the test is not equal to the true score. Your observed ability is not equal to your true ability because something has intervened. So the first thing we need to do, as I've indicated, is distinguish between observed scores and true scores. In fact, observed scores equal true scores combined with error. And I can't say that word any other way, I'm sorry. Error. E-R-R-O-R. Okay. If we take a look here, we have X observed, which represents an observed score, equals X true, the true score, combined with plus or minus some amount of error. We can reconfigure that equation so that it isolates the true score and indicate that the true score equals the observed score combined with some amount of error. The reality is that all observed scores include error. The task of those who manufacture measuring devices, and there are obviously thousands and thousands and thousands of measuring devices, and the objective and task of researchers who use measuring instruments is to minimize the amount of error that leaks into the observed scores, that leaks into the instrument. You understand, for example, that a measuring device and the scores that it generates are linked inextricably. One is only as good as the other. Yes, the observed scores that derive from your watch are only as good as the watch that you use. They're only as accurate, for example, as the watch that you have, and so on. So that the scores that derive from measuring devices used by communication or social researchers more generally are only as good as the measuring devices themselves. So we can distinguish, first of all, between true scores and observed scores, and second, observe that true scores equal observed scores combined with some amount of error. Now, error can be of two kinds. Error can be systematic, and error can be random. Error can be systematic, or error can be random. Let me talk about systematic error first of all. Systematic error is unidimensional. That is, it always occurs in the same direction. And it is consistent in magnitude. It's always the same amount. Let's go through an example of this. We have, let's talk about a set of scales that you have at home. These generate XO, observed scores. You get on your scales at home and they read 174 pounds. You are beamed Star Trek-like to a physician's office. And this physician happens to have a set of scales that were handed down by the gods that are error-free. And you weigh yourself on these magical scales at the physician's office. And because they are error-free, handed down by the gods, we can treat these as true scores. You get on those scales. First of all, you drop everything you're carrying. Then you put one toe lightly on the scales and make contact and friends with the scales so they treat you nicely. And then you hold on to somebody and you get the other foot on the scales and then you let the other person go. But even when you do that, the physician's scales indicate that you weigh 177 pounds. You go away dejected because you now weigh 3 pounds more than you thought you do, and you live in a culture that's fixated with this. You measure yourself at a second point in time at home, and the scales say you weigh 172 pounds. You are once again beamed, Star Trek-like, immediately down to the physician's office, stand once again on these magical scales, and those scales tell you that you weigh 175 pounds. You get on your scales at home a third time, and they tell you that you weigh 175 pounds. What is your true weight? We can all very quickly say 178 pounds, and we can do so because the error that's involved between the observed scores and the true scores is systematic. It's always in the same direction. That is, the observed scores always are less than the true scores. And it's consistent in magnitude. The difference is always minus 3 pounds. So that we know that this true score is 3 pounds greater than the observed score. Yeah. Are there any questions about systematic error? Yes.
Why is it minus 3 if it would be 178?
Well, it's just a matter of how these scores are configured. I've simply said that the observed scores are 3 pounds less than the true scores. So if we're looking at this, if we want to compute this true score, it's 3 pounds more than the observed score. It's just in the way that the issue has been configured verbally. If we conceptualized of these observed scores as estimates of the true score, we could conceptualize of a target. And at the center of this target is the true score, a true score of whatever we're measuring. Systematic error clearly is inaccurate. That is, we're not our scales at home did not measure precisely true body weight. So we were missing the target, missing the bullseye. But we were doing so in a consistent way. The point of this is that systematic error affects the accuracy of scores, the accuracy of observed scores. And because it affects the accuracy of observed scores, it is associated with measurement validity. It is associated with measurement validity. We will talk much less about measurement validity than we will of measurement reliability. But researchers can introduce invalidity into the scales that they use. Each of you, I presume, took the SAT. Some of you will want to go on to graduate school, and you will have to take the GRE or the GMAT or the LSAT or some other standard, the MCAT, whatever it is. But many of you will be required to take some standardized test. I suspect that each of you is aware of the debate that surrounds those standardized tests. It's quite normal for graduate programs to use the GRE as part of its evaluation of applicants. Some programs do not use the GRE at all. And it's not because faculty in those programs don't understand, cannot interpret GRE scores. It's because those faculty have concluded that the GRE is invalid. That it's invalid for perhaps a number of reasons. One argument is that the scores on that the test itself, and so the scores on the test, are systematically affected as a function of race or ethnicity. Another argument is that those scores on the test are systematically affected by gender. Another argument is that whatever the scores, whatever the test is measuring, and whatever the scores purport to be a measure of, is something other than scholastic aptitude, or something other than intelligence. If you were to have taken the GRE, I don't know, certainly 20 years ago, I guess, 20 years ago, or 30 years ago, whenever I took the GRE, 25 years ago, you would have discovered that the test included two sections, as I believe the SAT does. It included a verbal section and a quantitative section. Conceptually, what that says is that scholastic aptitude, if that's what the instrument purports to measure, equals quantitative ability plus verbal ability. And the operational definition of that becomes that your score on the SAT or the GRE or the GMAT, whatever it may be, equals your score on a quantitative section plus your score on a verbal section. Yes? Well, at some point, somebody came along and said that's not what scholastic aptitude means. This is not a matter of it doesn't mean that operationally. That is, when you think of this thing, scholastic aptitude, and you try to define it conceptually up here, it involves more than quantitative ability and verbal ability. Some people argue that it includes as well something called reasoning ability. And so a generation of test takers, those who took the GRE, found that the test comprised three sections. a quantitative section, a verbal section, and a reasoning section. And that is to argue then that scholastic aptitude equals quantitative ability plus verbal ability plus reasoning ability. More recently, the test has been changed again. If you took the test today, you would find that there are in fact 3 sections to the test, but those sections are a quantitative section, a verbal section, and a writing section. And that is to argue conceptually that scholastic aptitude equals quantitative ability plus verbal ability plus writing ability. Not everybody here can be right. Not everybody here can be right. That is, this thing called scholastic aptitude is either one thing or it's not. It's either verbal ability plus quantitative ability, or verbal ability plus quantitative ability plus reasoning ability, or verbal ability plus quantitative ability plus writing ability, or something else. And to the extent that it's one of those things and not the others, then those other measures are invalid, because they include or exclude constituent parts of what you and I understand up here to mean scholastic aptitude. So researchers can introduce invalidity into their measures in a variety of ways. They can introduce ethnic bias, gender bias, or simply in a wider way define the construct that they're attempting to measure inappropriately. In a more operational way, researchers can introduce invalidity into their measures as a function of the difficulty of the test. Because test difficulty, or test ease, will affect the observed scores in a systematic way. On an easy test of arithmetic, everybody should score relatively higher than their true ability, and on a difficult test of arithmetic, everybody should score lower than their true ability. So, first of all, we can distinguish between, and should distinguish between, observed and true scores. And recognize that observed scores include a true score component and an error component. That error can be of 2 kinds. The first is systematic error. And systematic error affects the accuracy or the validity of scores. And we've talked generally about the issue of validity. And the reason we won't talk about it any further is because it's a difficult issue to resolve. You can't just go out and measure something statistically. You cannot bring in an expert or some cookie cutter and impose it on the measuring device and say, yeah, this is in fact a valid measure of scholastic aptitude or intelligence or communicative competence or anything else. It's a conceptual argument, often. It's an argument that the test is biased in some way, or the test does not include constituent parts of the construct, or it includes bits and pieces that are not part of the construct. But it's a conceptual argument. It's not a statistical argument for the most part. Are there any questions about systematic error or measures or issues of validity? Let's then talk about random error. Let's talk about random error. And let's go back to our example or at the physician's office. You get on your scales at home. Your scales read 174 pounds. You go to the physicians, magically beamed down there. You get on these magic scales, handed down by the gods, error-free. And once again, the physician's scales indicate that you weigh 177 pounds. You weigh yourself at home a second time, and you weigh 172 pounds. And you go down to the physician's office, and the physician's scales tell you that you weigh 170 pounds. You get on your scales at home a third time, and they tell you that you weigh 175 pounds. What is your true weight? You don't know. You don't know because this time the error fluctuates. It is sometimes positive error, and it is sometimes negative error. It also varies in magnitude. That is, in a more general sense, random error varies in direction and varies in magnitude. So that random error affects the consistency of observed scores. And if you're talking about the consistency of observed scores, you're talking about issues of measurement reliability. Let me briefly go through this again. Error can be of two kinds. Systematic, which we've talked about, unidimensional, consistent in magnitude, affects the accuracy of scores, and so is at the root of measurement validity. Error can also be random. Random error is just as likely to be positive as negative, and it varies in magnitude. That is, it affects the consistency of scores, and so is fundamental to the issue of measurement reliability. If we were to return to the example of the bullseye, the error would not be, as it was before, systematic. Random error we could represent like this. Varies in magnitude, is just as likely to be in one direction as another. And so affects the consistency of scores, which is an issue, which is the issue of measurement reliability. If we think more about random error, where does it come from? Where does it come from? Because the sort of first issue the first issue that comes to mind if you talk about an error component in scores and argue that it is the responsibility and the objective of researchers to reduce, to minimize the error component of observed scores, then you have to, I think, preliminarily at least, ask where this error arises from. It's not a rhetorical question, so while you're thinking about that, let me make a couple of observations, more general observations, about the nature of this error, about the nature of this of measurement reliability. First of all, as I said at the outset, all observed scores, all instruments are susceptible, include an error component. It is not reasonable for you to expect that the measuring devices that you purchase, that you use, or the measuring devices that researchers use will be error-free. Secondly, when discussing measurement reliability, we've talked about it as if it's a thing that affects an instrument in a uniform way. That we could pick up one instrument and say, this is unreliable, and the scores from it are unreliable, and perhaps we could measure how unreliable. And then we could pick up another instrument and do the same. The problem is that that unreliability, or the reliability, is not distributed evenly across the scale that the instrument uses. If let's think of a thermometer used to measure body temperature. The manufacturers of thermometers are not concerned whether or not their instruments, their thermometers, measure your body temperature accurately at 72 degrees. Because at 72 degrees, you're gone. Yeah. You've said sayonara. Or at the very least, you're in obvious distress. And we don't need a thermometer to measure precisely how much distress you're in. In the same way, manufacturers of thermometers are not interested that their devices be reliable when measuring body temperatures of 119 degrees, because at 119 degrees, you're gone as well, or as I've said, at the very least, in obvious distress. The manufacturers of thermometers, as a measuring device, are interested that their devices be reliable and valid within a limited range. A limited range that represents sort of average and common body temperatures. 97 degrees to 104 degrees. I don't know. 97 degrees to 103 degrees. Who knows? But the manufacturer knows. The same is true of automobile manufacturers. If some of you look at the speedometer in your car, you'll find that there are no values between 0 and 5, or perhaps between 0 and 10. Doesn't mean that you go automatically to 10 miles an hour. You know, I've got this freak car, I've got this magic car. It skips all the speeds between 0 and 10 miles an hour. No, it doesn't. It goes through those speeds. The thing is that those speeds are irrelevant. They're practically irrelevant. And so the manufacturer of the speedometer has recognized when those values between 0 and 10 are not included, has recognized explicitly that the thermometer, the measuring device, is not designed to generate accurate or reliable estimates at such low speeds. The same is true at high speeds. Some of you have thermometers, have speedometers that don't measure speeds a bit above 140 miles an hour. It's not because your car won't go above 140 miles an hour. It's just at that speed, you're going fast. You're going fast. And you don't need to know how fast. The speedometer is designed to be particularly reliable and particularly valid within a limited range. 15 to 55 or 85 miles an hour, whatever it may be. Because that's the range when it's important for you to know accurately how fast you're traveling. The point I'm making here is that while you and I previously talked about instrument reliability or unreliability as if the entire instrument was affected in a uniform way, that is not the case. All instruments are more unreliable at the extremes. All instruments are more unreliable at the extremes. Let me say this. None of this is in the text. Some of you who aren't might want to make a note of it, because it might be on an exam. Oh my God. Somebody in a moment is going to say, could you just repeat what you... No. All instruments become more unreliable as you approach extremes of those instruments, because instruments are simply not designed to measure freak events. If you scored somewhere in the neighborhood of, let's say, 1100 on the SAT, and a friend of yours scored 450, and you both take the test 2 or 3 times, your friend's scores are likely to vary more than yours, because you've scored in the sort of middle of the instrument's range of values, and your friend has scored at the extreme. Your friend is a freak. In a nice way. In a scholastic aptitude way. And those extreme scores are simply more vulnerable to error than are scores at the center of a testing instrument. So those are a couple of general observations about reliability. Let's return to the issue of where does unreliability, that is, where does random error derive from? That was a horribly constructed sentence. From where does random error derive? Let me put it this way. If you take a test, any time, well, let me become even more real worldish. Often you take tests. You take tests routinely. And it's not unusual for you to get the test back and be surprised at the score you achieved. Sometimes your score is higher than you imagined it would be. And you don't, under those conditions, I know most of you actually do, there are a couple of you under those conditions who don't run off to the instructor and say, I think this was a bad test because I scored a lot higher on it than I thought I would. So let me take another test so that you can get my true score. Sometimes the score you achieve on the test is less than you believe you deserve. That is, it is lower than you believe your true ability to be. Why does that happen? That is, when that situation occurs and you go off to the instructor of the course and say, I don't think this score that I have is reflective of my true ability. What's the because?
Maybe you're sick, or maybe you have like another situation going on, or you weren't able to think that day, or you were late, or something.
The examples that you offer, that you feel sick, or you were rushed, or there were other things going on that distracted you in your life. Those are all factors that introduce random error into scores. And we could also talk about respondent fatigue. Yeah. If your tired, the likelihood of random error being included in your scores increases. If you are in a bad mood for some reason, it is likely that you will be, more likely that you will be penalized by random error. Those people who are in a good mood are more likely to be rewarded by positive error. And the importance of this, and you know this, you wake up in the morning, you go to drive out, and there's that pet cat of 12 years just keeled over in your driveway. It happens to cats, and I mourn every one of them. And you become saddened. You know that the likelihood now is that you will do less well on a test that day than if your cat were alive and well and destroying your home or somebody else's home, as cats will. Yeah. In the same way, if you are tired, the likelihood is that you will be penalized by negative error. You will do less well than you would otherwise. Yeah. And the significance of these sources of random error is that they are not under the control of the researcher. Recall at the very outset of this discussion, I argued that the researcher's objective, a researcher's objective, is to reduce the error component in the observed scores. That is, to make the instruments that she or he uses as reliable and as valid as possible. Well, clearly there is a limit to the researcher's ability to achieve that objective, because some sources of random error simply are not under her or his control. You and me, respondents, test takers, bring some sources of random error with us. Our mood, our level of fatigue, and so on. Some sources of random error, however, are clearly under the control of the researcher, because they're inherent in the test. One source of random error inherent in the test is item ambiguity. Item ambiguity. And you know this, because each of you has taken any number of tests, multiple choice tests, true, false tests, whatever it may be, essay exams, in which you have come to a particular question and you've read it and said, I don't understand what this means. And you reread it and you still don't really understand what it means, so you guess. And when respondents guess, getting the question right or getting the question wrong is not an issue of their ability, it's an issue of luck. So that some people with high ability will get the question right and others will get it wrong. And some people with low ability will get the question right and some will get it wrong. And that's a function of random error, because to the extent that a test item is ambiguous, each test taker may as well flip a coin. If it's a true-false question, each test taker literally may as well flip a coin. And clearly some people with high ability will be lucky and flip heads and choose correctly, and others will be unlucky and flip tails and choose incorrectly. But that will be also true of people with low ability, and there is no way of tying rightness, wrongness of answer to true ability. A second source of random error that is inherent in the test itself is the length of the test. the most unreliable tests are single item tests. Tests that include one question and one question only. And these are a favorite of some researchers. Because common sense would say to you, if you want to know how much a person likes a particular candy bar, surely the best way is to say to the person, how much did you like the candy bar? It turns out that that's not the case. Because if you ask the person how much they like the candy bar, they may think, do you mean how much I like the nuts in it? Or would it be better without the caramel? Or should there be more chocolate? Or would it be better with that dark chocolate than the milk chocolate? See, I'm English. We eat a lot of candy. I've got this very complex view of candy bars. Nuts and caramel. And is it better when it's cold? Would it be better if you put it in the refrigerator? God knows people in Scotland now deep fry any candy bar you can. Even deep fry pizza. There are places that will deep fry anything. But deep fried Twiggers, deep fried Snickers bars, just coat them in batter, stick them in fat, and you've now made a 300 calorie candy bar into a 2,000 calorie candy bar. All that on top of 28 pints of beer, and that's a typical Scottish diet. I know. They actually do have the worst diet in Europe. So The point is that single item measures are notoriously unreliable. What you need, this is, I think, apparent to you. If you had gone to take the SAT and found that there was a single question in the verbal section and a single question in the quantitative section, you would have been, I hope, dismayed. If you get this right, you've got high ability. If you get it wrong, oh God, oh no. So, obviously the solution to these two issues is, on the one hand, to seek to ensure that the items that you use on tests are unambiguous, and on the other, to generate relatively long tests as opposed to relatively short tests. The trade-off here is between the length of the test and respondent fatigue. Because clearly, particularly in non-academic settings, that is, in settings where you're simply participating in research, the longer the test, the more likely it is that the sort of screw you phenomenon will click in. That at some point, you're answering these questions as best you can, 2, and you read it 5, and then you read it 2, and you read it 3, and at some point, let's say this is on a scale of 1 to 7. At some point, you just go 3, 3, 3, 3, 3, 3, 3, 3, 3. I've conducted research. I know this. It's the risk of using very long tests, and sometimes it's necessary to use very long tests. But each of you has been in that situation. Each of you has gone to a new physician and said, could you just fill out these forms while you're waiting? And you go through it, and you just, I'm not even reading the question. Have I had this disease? No. I don't even know what the disease is. I didn't read it. I just saw it was a column that said yes and a column that said no, and I just checked the no's. And you take it up back after 45 minutes of responding to it, and the person at the desk says, oh, well, you didn't answer the questions on the back. And you find that each page now has a reverse side with even more questions. And each of you has been in this situation. So while single item tests are notoriously unreliable, and while the obvious solution to that is to generate relatively long tests rather than relatively short tests, there is a trade-off there, a limiting factor, and that is respondent fatigue. Because at some point, respondents to long tests simply become tired of physically tired and mentally tired of the test, and provide answers that are simply unrepresentative of actual behavior or actual preferences or whatever it is that you may be measuring. Are there any questions about random error to this point? Hearing none, we will talk more about this issue next time. I will remind you that it is not an issue that is covered in the text. If you wish to read more about this topic outside of my lectures, many introductory research methods texts take up the issue, but often it's in a relatively complex way. But there are a host of those, and I'm sure that you will have no difficulty finding them. But we will talk more about measurement reliability, how to assess measurement reliability, and so on next time. Yes.